All right, so with this video, I want to quickly review this idea of function composition that hopefully people have seen before, and then relate that to linear transformations and in particular, invertible linear transformations. And so if I have two functions, say f and g, then function composition denoted oftentimes like this or this, something like f of g of x, this is the one I like, means that you first apply g to x and then f to g of x. So for example, if maybe let's say f of x is, I don't know, 5x and g of x is x squared, then f of g of x would be, first I would perform g of x, so I would have x squared, and then I would multiply it by 5. And similarly, I could also do something like g of f of x. The order doesn't, the order does matter. The composition can just be defined for both. And so what this would mean is that I'd perform f of x first. So I would do 5 times x, and then I would perform g on f of x, which means that I would take this and I would then square it. So that's, I find out what 5x is, whatever, and then I square it. And so let's say that x is equal to 3, then f of g of 3 means I first square 3, so that would be 9, and then I multiply it by 5, so I get 45. And if I wanted to do g of f of x, then I would first instead multiply x, aka 3 by 5. So when I do that, I get 15. And then I would do g of 15, which is to square 15. So whatever that is, I can't remember off the top of my head. Maybe 225? I don't know. Either way, the answer is 15 squared. Okay, so I'm going to say that we can do a similar thing with linear transformations. And so recall, if my transformation t, and this time let me say from Rn to Rn is linear, then we know that I can represent this transformation t of x with a standard matrix A. And in this instance, then A is n by n, since my transformation is from Rn to Rn. And so if I can represent T with this standard matrix, then that means I can ask whether or not this matrix is invertible. And that in fact is the same as asking whether or not my linear transformation is invertible. And so let me formally define that. So I'll say a definition, a linear transformation T from Rn to Rn is said to be invertible if there exists a transformation S also from Rn to Rn, stretch that, for all x in Rn, S of t of x is equal to x. And then in this instance, we call the transformation S, and I'm the inverse of t, and so we can denote it in this way. Okay, and so how do we form S? Well, what we do is we would let S be represented by the standard matrix A inverse. So in this instance, the transformation S of x would be equal to A inverse times x. And so notice here, if that's true, if f of S of x does equal A inverse of x, then S of t of x is equal to S, and we know that t of x can be defined by this matrix multiplication, A times x. But we're saying that S, and so when I do this I get some vector, and we're saying that S of any vector is equal to A inverse times that vector. So this is equal to, by definition, A inverse times A of x. But we know that matrix multiplication has this associativity property, which tells me that I can do A inverse times A first and then multiply it by x. But here, by definition, we know this is the identity, and I multiply it by x. Okay, by x. And like we talked about in class, if I take the identity matrix times a vector x, it is just x. And so that confirms that if I define S in this way, where S is the transformation represented by A inverse times x, then it is in fact an inverse of my transformation.